Hello folks, fellow YouTubers and friends. We're here at Boomtown Laboratories and we're working on a heat engine here. First off, I'd like to introduce you to my father-in-law. Where is he? There he is, Nicholas. Alright. That's my father-in-law, Nicholas Navarro. He's 3 years younger than me. And my mother-in-law, sitting over there in the chair. And my wife's cousin, Junior. Okay. All right, folks. What we want to do is we want to get back, if I can get this camera going again. There we go. I want to get back here and discuss a few situations I've got going on here. In building heat engines, like the conservation of energy, laws of conservation of energy. Okay, number one, energy cannot be created from nothing. Well, hell, you can't create anything. Nothing. Got to have something. But there again, law number two, energy cannot be destroyed. Well, let's see. Now, if you can't make energy from nothing and you can't destroy it, then what happened to the energy you used yesterday? Or this morning, for example. Well, in comes the third law of the conservation of energy, and that is you can change its size, shape, form, and or direction. Any one of the three. Any two of them together, or all three. So, when you not create, but change energy's form from one form to another, like for example everybody says light is heat and heat is light. Well, okay, but if we take heat and we change it form, not necessarily change its form, but for example we take it from fire and we heat water, well, we're storing the heat in the water or in the air. When you compress air, a lot of people say there's no such thing as free energy. Well, on this radio on Saturdays we discussed this many times. There's no such thing as energy that is not free. After all, you are swimming in it. Every day when you walk around, your body is moving energy out of your way so that you can get somewhere. Air contains a lot of heat. Like right now, it's roughly 60, 62 degrees here in the shop, and if I was to turn my air compressor on and let it run to the fill of the tank, the tank itself would not only be hot, but the cylinder head on the compressor would be hot enough it would blister you. What it's doing is it's taking what little bit of heat that's in the air and compressing it into a tighter container. The temperature goes up, but the amount of heat does not. You're just compressing the heat in a smaller container. Therefore, when the compressor cools off and the heat dissipates and you let that air out, that air is a lot colder than when you compressed it. Now, I use cold air a lot, and I'm going to be doing something to my compressor to produce even colder air, and I'm going to show you all that. But here's the main thing I want to discuss today is check valves. Check valves are things that let liquids or gases travel in one direction but not another. They stop the flow. Now, the thing is, I've been playing because I've checked out a few check valves that you buy on the market, and they have a lot of resistance. And what I'm trying to do is create a check valve that has very, very little resistance in one direction and will stop the airflow in the other. Now, this one I've slightly messed up. The cork is not fully the size, but it works great, but not good enough for what I want. So if I blow through it, there's no resistance at all. If I suck through it, this way it stops completely. And I've got one here. What I've done is I've used different types of gasket material. I've used a cork, and here's some type of neoprene. Now, neoprene's a little stiffer, so therefore it causes a little bit more resistance than the cork, but it's stiffer, so it'll take more pressure this way. Now, here's the thing a lot of people don't understand about check valves, okay? For example, the pipe has a thickness to it. You can see that. So the outside diameter of the pipe is bigger and has more square inches of surface area. Now, just say, for example, this is a pure example now. Let's just say that, here's one bigger so you can see what I'm talking about. Let's say this is 1 square inch, but yet the opening is a half a square inch. That means 10 pounds of pressure here is going to take 20 pounds of pressure over here just to open this valve. So that 10 pounds of pressure will hold back 20 pounds of pressure over here. So when you're building a check valve yourself, you can actually design it to do what you want it to do by simply knowing the surface area of one side and the surface area of the other side, and you can control how much pressure you can hold back, how much you're going to have on this side just to open it up to let it through. So when you're building a heat engine, if you want to get technical and get down to your pressures, that's the way to do it, okay? Now, if anybody knows a simpler and easier way to build these things than what I've done, I would appreciate some comments or even a video response. That would be great. Now, the way I do it, rather than cut the material the size of the pipe, what I do is I put a little JB Weld on the material and then put the pipe down on it until it sets up. Then when I get through, I use my aviation strip or my scissors. What I'll do is I'll take the scissors and trim off the excess as much as possible within reason. And then where the JB Weld squeezes out, I use the aviation strip, so they cut right through the JB Weld a lot easier than the scissors, okay? Then, when it's done, you take a belt sander. Do not use a grinding wheel. Good God, Miss Agnes, I have seen so many people use grinding wheels on non-ferrous metals and plastics. That is the worst thing you can do. Non-ferrous metals do not grind, they melt, and they deposit residue inside the pits of your grinding wheel. And a high-speed grinding wheel can, and I know this from experience, not myself, but friends of mine that have half their face tore off because of a grinding wheel flying at 6,000 to 7,000 RPMs, got out of balance because of the residue from the copper or brass or whatever they were grinding, or plastic, got out of balance and literally exploded and took half their face off. So don't do that. I use a belt sander or a sanding wheel or a drill motor, whatever. They turn to low RPMs. They're not going to fly apart and hurt anybody. I mean, you know, you might get a blood blister out of it. But anyway, you take the belt sander, have the blades coming to you, and put it down like this so it comes to you. That way it do that. And you want it down on a little bit of an angle, like 5-degree angle, and just barely do it until it just touches the plastic of the PVC pipe. And that way it gets it clean and then slide right in to your deal. Now these things work really great. No problem. Cannot suck back through. They work great under low pressure. Now high pressure could cave the cork in. Okay, that's why I did both the cork and the neoprene. So the neoprene will stand a lot greater pressure back here without collapsing. Now here's another thing too. When you take your material and you put your JB Weld on it, all right, what you want to do is you make a straight swatch of JB Weld, and then you place your down on it, and you want it to cover just about, depending on how much power you want it to have as far as holding back and how much and so forth, a quarter of the diameter to make a straight line across, and that's where you put it down and let it set. When it does, then you cut off the excess. And what that does, if you put your JB Weld here, okay, then the material has got to bend up, and it has nothing to bend against, so it'll actually try to bow here and make it difficult to open. So you want your JB Weld in a straight line so it opens up very easy. Okay. All right. Okay. Enough of that. Anybody got any better ideas? I'd appreciate it. Now, what we've done is my father-in-law, I call him Poppy, even though he's younger than me. He came up with these styrofoam balls. No, they work great. In fact, where's that piece of pipe there? Junior, where's that piece of pipe? The pipe, chica. Oh, there it is. Okay. Now you'll see that on a 1/2 inch PVC pipe, the ball will not go in it, but it will. No, it won't either. It won't go in the cup. We had this right, Poppy. What do we do with it?
What are you looking for, Ben?
Oh, I had this thing where it worked. But I can't figure out how I did it.
¿Qué buscas, tío?
Dice que lo que va ahí.
Alright, forget that. Anyway, you can use a styrofoam ball in there as long as it covers the end of the pipe, but will fit inside of your coupling. And what you're going to have to do, because if you had another piece of pipe here, it would come up and hit both of them and do it. So you're going to have to drill a hole back here, put a piece of wire through, and seal the ends with JB Weld. Okay. Well, the main thing I'm trying to do is talk to you about check valves and so forth, and moving materials from one place to another, because that's what you're trying to do. You're trying to move energy. Now you're storing the energy in water or something, or metal or whatever, and you're storing the heat up, but then you want to get the heat out and move it to a different location. Now most times it's to a piston or something that turns or whatever, and you're going to have that energy turn that wheel or move that piston, but then you've got to expel it. And that's the one thing I'm really picky on. If people don't understand about a heat engine, okay, they think you put heat into it and the engine runs. Well, the heat is what causes it to run, but what really causes it to run is the fact that you can get the heat out of the engine as fast or faster than you can put it in. I mean, you take a heat engine, you jam it full of heat, it's going to run for about 2 or 3 seconds. Maybe even if you build it right, it might run for a minute or two. But eventually it's going to stop. If you cannot get the heat out as fast as you put it in, or you put in more heat than it can take out, it will stop.
Yes, okay.
You've got to have the ability to get out more heat faster than you can put it in. That's why the old steam train locomotives work so well, is because they expel the steam, the heat, out into midair. They had no restriction. Nowadays they try to recycle the water, which is a good thing, and if done right, it's very great. You conserve on water, and you also conserve on heat, because when you condense that steam, you've already got your water back at boiling point. Now, my pet thing that I'm working on, and everybody knows it, is what I'm called a cold steam turbine. Cold steam being that we can produce steam, okay, at room temperature. If you reduce the pressure on water, you reduce the temperature at which it boils. Now, if I took a jar and filled it full of water with no air bubbles, took it underwater, filled it, and put the lid on it, and it's a mason jar. Thing is, with a mason jar, they're designed to handle vacuums, not pressure. So anyway, you take the vacuum jar, you make sure the lid is loose, like so. Fill it full of water. Underwater, you put the lid on, and you put the ring on it, okay? And, oops. I'll get it right in a minute, folks. Yeah, put the ring on. There you go. But you don't get it tight. Back it off just a little bit, bring it out of the water, turn it upside down, and heat it. Now, as the water gets to a boiling temperature and starts to boil, it creates a cold steam up here. At first it's hot, because you're talking room temperature. And I had to wear gloves to do this. But anyway, as it boils, it's being replaced with steam. And as it gets down, it boils more and more and more and faster and faster, because you get less and less air in here. You have no air at all, actually. And when it gets down to a certain level, then that's when you tighten it and let it cool. Now, as it cools, it creates a vacuum and sucks the lid tight. Now, when I did this, it actually created so much heat it burnt the seal. So the vacuum only lasted about 3 days. If I had not burnt the seal, it would have lasted a long time. Well, I mean, years even. That's been my biggest problem with the cold steam turbine, is trying to maintain the vacuum. Now, what happens is that water, once it cools, no matter what the temperature, the water remains at the boiling point. The worst thing about steam engines is you're taking cold water, you have to heat it up to the boiling point in order for it to get it to boil. Now, once the water is at boiling temperature, then it only takes 840 BTUs per pound of water to turn it into steam. Now, what you have here is a pure vacuum, or close to it. In other words, the only thing in there is water moisture. So your vacuum is somewhere between 14 and 15 psi negative. All right. So any steam reduces that negativity and pulls it down to 11, 12, maybe 10 psi. Now, therefore, that negative 10 psi is no power to turn something. But the thing people don't realize is that steam, that's churning that water has got unbelievable power. So you're not using the steam per se to actually operate a steam engine. You're using the turbulence of the water. And we're going to do this at a later date. What I'm going to do is drill some holes in here and put a couple of coils on it to heat it off, to get the steam off. The heat off, like I said, a heat engine works by taking the heat out of the engine as fast or faster than you can put it in. Now we're going to take a piece of styrofoam, put it in here, fasten a magnet to it, and we're going to try to fix it so it doesn't move all around, just jump up and down with the water. And we're going to put a copper coil here and show you that it will make electricity. A tea candle will make unbelievable amounts of electricity. The power of this is unreal. In fact, when I did it, I didn't have anything in here. I had about an inch and a half of water, and I passed my torch card just that fast, and the thing busted with steam so fast it almost knocked the jar out of my hand. And we're talking about, I can take a torch, pass across my hand for an hour just like that, back and forth, with no heat that I can feel, but the water can feel it because it is at boiling temperature. If the room temperature gets warmer, the water will boil so lightly that you cannot see it with the naked eye, but it will actually produce steam, keeping the pressure at exactly what is necessary. So the water 24/7 is at boiling temperature until the temperature of the room and the water reaches about 50 degrees. There's 1,000 millibars at sea level pressure, give or take. At 4 to 5 millibars, water boils at 55 degrees Fahrenheit. And the atmospheric pressure on Mars is 5 millibars, water boils at 55 degrees. My vacuum pump is a 3 cubic foot per minute, 2-stage vacuum pump. It will pull down to less than 3 millibars. So I can get water to boil at 50 degrees. However, the thing is, at room temperature, the water in the container, in the boiler, is always right there at boiling temperature. Whatever that pressure is, that's the boiling point. Therefore, I do not need to add any heat to the water to raise the temperature of the water, only BTUs in order to get it to boil. That's why it boils so fast. Now, what I'm going to do is I'm going to put copper pipe down here coming out with a ball on, so I put a tea candle. I'm heating a very, very small amount of water. And you're going to see an unbelievable reaction. I'm going to do this today. I'm going to drill holes in here and make the coils. If anybody'd like to see me making the coils, I'd be glad to make a video of that. It's so simple, it's pathetic. I use salt. Some people use sand, some people sugar. I prefer salt. In medium-sized copper pipe, I prefer clay sand. In medium-sized, rather larger copper pipe, but really small copper pipe, I like sugar. What you do is you fill your pipe up with your salt, sugar, or sand, and then that way you can bend it around another piece of pipe without it kinking on you, and it works really great. I mean, it's almost stupid for me to make the video of it, So, so many other people have already done it. Anyway, so much for this video. We're gonna get work on this and see if we can't make a couple of decent videos and show you a few things. All right. Everybody have a great day. By the way, it's January the 15th, 2019, and it is almost 4 p.m. in the afternoon. Have a great day, and I'll talk to you folks later. Sorry about this video being so long, but I just wanted to get all that in. Thank you.